I forgot my mic was on. It's okay, it's not really that. I don't know, like, why my mic is so dead, you know. Anyway, just a quick update. Wait, I wanted to get... Oh, where is... Okay, so this... I gotta just kind of set this up really quick. My stream. Short stream. I'm gonna have something to eat, and I have to go to work tonight. And there's a good chance that I might be coming back on the stream to talk about this, what I'm gonna talk about right now, actually. My voice is dry. Let me just back this off here. We got some music playing in the background. Let's go to, I'm gonna bring up my illustrious picture here. And then I'm gonna bring up, paint, which should come up. It does, it's a little bit messed up, I'll fix that. So, what you see here is what's called the Mandelbrot set. I think I'm going to sneeze. But anyway, so you can see there's a lot of repetition. I'm not monitoring my stream, by the way. Well, I sort of could, but I'm not monitoring anything. This is going to be a quick stream on my update. So my project is going pretty good. I've got more of the bracing set up for my mirror complex for the interferometer is going to be all built on top of a platform, and that platform is movable inside and outside of a computer case that I'm building for it. So yeah, it's taken me a good couple of weeks, or probably a month, to get all to, probably 2 months. I don't know. It's just really, I'm getting burned out from building it, actually. I'm thinking of these things. It's really weird because in the process of building this thing, I had some problems that I really didn't want to solve. And I had more problems that I didn't want to solve. And I'm like, oh, I gotta do this, and I gotta do that, and I don't know what to do, you know? And so I'm thinking, maybe there's another way. And in that process, I've had these weird thoughts come into my head, just really strange, just right out of nowhere. And they were like, well, you could do this, you could try this, you know? And so, well, I got plastic. A lot of everything is made with plastic inside, except for the mirrors, stuff like that, whatever, springs, metal, there's some metal. So I was going to use threaded rods to connect the mirrors to, so that you can take the threaded rods and you can adjust them, right? And so evidently it's going to be a little bit more complex, but I don't know how that complexity is going to work yet. The reason why, so there's, instead of using there's like 12-inch connected threaded rods, and then you connect the tuning screws on one end, and you tie the other end off with the springs, such like that. So you make a course adjustment with the threaded rod, and so the course, I'm talking about the mirrors. There's 2 mirrors on the top. One mirror bounces the signal down to the beam splitter, and so on and so forth. So you've got 2 mirrors on the top. Why 2 mirrors? Why not just send the light source down to the beam splitter? So the reason for that is I don't, when I do the beam splitter, I don't want to move the beam splitter. I want it, the beam splitter needs to be centered and focused into the interferometer. You don't want to touch that thing. Once it's there and it's lined up, you're done with it, okay? But what's going to happen is that the inside of the computer case is it's going to be temperature cooled. It's going to be vacuumed out, the air. Some of the air is going to come out. That will help to lower the amount of moisture in the air, I'm hoping, is what I'm thinking. I just need to evacuate the air. It's like a lot of this stuff is control system. And so, and it has to be equalized inside of the entire case. And it's not just a computer case. The computer case was split in half and widened out so that it's actually a foot wide. And I'm using the computer case as and then I got a separate top for it. Yeah, there's a separate. The computer case is upside down when it connects to the wood that's underneath, and then there's another computer case top that goes on the top. That gets all connected, and this is all done with screws. And then I've got to devise a way. I got to make sure that I devise a method to seal the computer case. And so what I'm going to do is I've got some copper plating, but I think it's too thick. What I need is thin, like almost not like tinfoil because it rips apart, but I want a thin copper. Copper is soft, okay? So when you push the screws and stuff together in the metal, it acts as a seal for vacuum. None of this crappy foam shit. And so the other thing I'm going to do is I'm going to use this copper and I'm going to make a seal in a test box and test it and everything and see how the metal bends and all that kind of stuff to find out what my limits are before I actually go and do it with the actual machine. So anyway, that's all built on a separate platform, and the mirrors allow for one of the mirrors might be a grating. Okay, so you can't shine a grating into the beam splitter. You want to use slits, so you want to use a small circle, and you want to use a slit somewhere in there. So you put the slit before the beam splitter. There's things that can happen before the light goes into the beam splitter. So you've got the top mirrors, and then you can put a slit somewhere in there, maybe before you put the slit in. The second mirror is actually, which now that I think of it, it gives me an extra mirror, but the second mirror is actually the grating. And so what happens is it's a reflective grating, and it bounces off the grating, it goes down to the beam splitter. So the beam splitter is going to see the middle of the visible spectrum, the yellow whatever. And so this mirror has to be on an adjustable track so that it can move the visible light from the blue to the red. It moves the spectrum is what it does, and it's like really, really super. I mean, the change is so small, it's just crazy. I've been working offline about how to set up the mirrors, how to see where the focus is on the spectrum. So it's going to be a spectrometer and an interferometer combined into one unit is what it is, and it's going to be tunable. And so the reason why I've decided this thing came to my head. It says use plastic instead of the threaded rods. So what I'm going to do is the plastic that I found, and I made 10 of them, by the way. I cut these out. Oh my God, so much work. But the plastic has got the little flat piece on the end. So I didn't, with the threaded rod, I had like a threaded rod, and I was going to have to attach a flat piece to the end of it so that the tuning screw can butt up against the flat piece and adjust the threaded rod from the outside. And so the threaded rods I got, they're crooked. They're not straight. They're old, and they're rusted, and they don't look good, and they're a little bit crooked. And so they don't, if you turn it, whatever, it's just crooked. I'm like, oh, what am I going to do with this problem, And so this thing about cutting up this plastic, it was this crap load of work. But I had 2 pieces of printers that I took apart, 2 big pieces. And lo and behold, the plastic that I cut out was 2 identical parts of the printers, and I got 5 pieces of plastic from each one, and they had, get this, they had the flat end on the end of the plastic on both ends, number one. And number two, you know, because when you cut it, it's a little bit flexible, but that's okay because the springs, I'm going to have 2 sets of springs on the outside of the plastic that is going to hold, it's going to create a tension. And there's that much space between the end of this piece of plastic that I cut. Oh my God, it's like so many things have happened in the building of this project with this plastic and these ideas that came in on how to do this. I cannot explain it. I cannot effing explain how it is that this thing is coming together. Because I had the design and the idea in my head, and, you know, granted, there's a little bit of inconsistency, there's a little bit of imperfection, you know, and so, but the imperfection is okay. You know, I'm able to maneuver that, and once I get the items, there's only going to be 2 mirrors suspended from this plastic. They'll be suspended from springs. The 2 mirrors are okay. The tuning cavity is really heavy because now I can see that the tuning cavity, I'm not going to be able to suspend that, I don't think. I might be able to. I don't know. It's kind of heavy. If I suspend it, it's going to create pressure on my support braces, which I think I'm going to have a problem with. So I may be able to put something on the base and have a stand for the tuning cavity. The spring, there's no springs inside. There's like foam inside of this thing. I was like, oh, this is a bit of a problem. And then I can make a couple of braces for that, and I can put some springs inside of the braces so that the tuning cavity sits on the springs, and that will give it, you know, and then I can adjust it with the stand. I can bring it up and adjust it and so on. That is sort of critical, or not, I think of it, because I got lenses on both ends. And so the lens, the center of the tuning cavity needs to be lined up perfectly with the beam splitter. So there's a thing there, and there's a, you know, there's an adjustment this way. So I probably do have to have some tuning screws set up for that. You know, coarse adjustment, fine adjustment. No big deal. I mean, it's all done with springs. This thing is, this is a work of art from, you know, I don't have a printer thing to make plastic printer stuff. So, you know, what am I going to do, right? So anyway, that's the story with that. I'm making progress with that. Okay, so here we have what's called a Mandelbrot set, but it's, you're looking at it from sort of like a 3-dimensional, okay? Now, on the left-hand side where these circles are, there's circles here, okay? And the arrow, which represents time, the very left-hand part of this, like maybe if I go with white and I go with a large line, in like this, and we draw, let's say we draw a line like this right here, and then we draw, I'm going to just put an arrow here and an arrow over here. And then we'll do let's do an orange line with a smaller arrow, and then we're going to put in like this here, and then another arrow like this here. All right, so what this arrow means, this is so significant that this discovery was made with this. This is just like, I'm venturing into territory that's never been done before. So the fact that what I'm about to explain to you really quickly, when I got to get some sleep and have a little bit of food, but I want to talk about this tonight. And so the right-hand side of the arrow of that orange space, that's the Mandelbrot set, Okay, it's kind of like a three-dimensional view. All right. When you look at the Mandelbrot set itself, there's a two-dimensional picture. Okay, but this picture right here, this is 3D. Now you got to get this. Okay, this is three effing dimensions. And why I say it like that, why I say it so emphatically, is because this, I'm just so flabbergasted. There is an equation that creates this, but there's another equation that also creates it. And it's called, well, there's a small equation, but there's a constant that happens. It's called the Feigenbaum constant. And we're going to get into these numbers. So anyway, this is three dimensions. Just remember that. All right, so then over on this side, we could just do a red line and then probably like that. Let's see, let's make it thinner maybe, and then use this. All right, so like what happens is there's this number, there's this thing that comes up like this. Oh, you cannot see that very well. It comes up like this. All right, then it splits into two pieces. Now what I'm showing you is something that's on a two-dimensional. Between the two lines, the two orange lines, imagine this as a box, okay? So like if I change it and then, you know, if I, it's a straight box, trust me. All right, so imagine that's a two-dimensional plane. So you've got this thing happening. It splits into two, all right? And then weird shit happens. It splits into two again. Okay? And then, yeah, you guessed it. It splits into two again. And what happens is that the splitting goes on to infinity. All right? It starts at a certain point. It has an origin. And then this curve comes up here. All right, so then what happens, we'll go with yellow, and we'll use that color. And I'm going to draw a line as best that I can. And what I'm doing is I'm drawing a line at the point where all of these things split. This is called a bifurcation diagram. And so there's a number that's associated with that. Let's use the green because I like green. Well, you know, you could go like here. This goes off into X or Y. I mean, and this goes off into Y, and then this goes off into Y. Okay, and so on and so forth. So each one of these splits have a number associated with them. Okay, so this would be actually, you know what? I don't know what it would be, because the number down here is actually t. It's time. It's not x. Now, this is something else that I've noticed a lot of streamers. They do this and they do that, and it's so freaking smart. Oh, we got this and we got that and everything else. They're not smart, okay? They're smart and they're good with stuff, but they miss the very important things that if you don't understand the entire picture, then you're not going to get the result you're looking for. So this is actually time, and I'm not quite sure, but I think this number up here, and I'm going to actually emphatically make that bigger, is x. It's not y. Normally in a graph, you have y on the up and down and x on the across, okay? But that's not what this is. Now you can infer when you do the computer program. You can say, okay, well, y is on the top, x is on the bottom, x increases, whatever. It's better to use the correct numbers so you know what you're looking at. So anyway, I probably should actually, I could just save this. So this is all on a plane. Now, somehow, I don't know, there's one video where they rotated this screen and they could show that the bifurcation diagram was the start of the Mandelbrot set, because it was flat. The Mandelbrot set was flat like this, but then they did something with the equations or something. I don't know what they did, but it's 3 dimensions. So this is the weird part about strange attractors and chaos and complexity theory. When you have a picture of something, I think that what you're looking at is you have this 2-dimensional picture, but I think what you're looking at is what's called a projection. You're looking at a 3-dimensional picture that is projected onto a 2-dimensional plane. What does that tell you? It tells you that t, time, is an extra dimension, and when you shift that information, now you've got well, where's the x in all of this? You know, you've got a point in space that's doing something, and it's moving ahead in time. That's all well and good. All right, so you've got this thing, right? So what I'm going to do is we're going to set up a new thing here, and I'm going to paint this. Can I do that? All right. So let me draw the graph. We'll use the lines here. This is what we're going to talk about tonight. This crazy ass shit, I'm telling you. It's so freaking crazy. This is going to be your graph, and we're not going to use t for time, all right? And there's also another graph. Let's do this red one. And we're going to put another graph down here. Now, I don't have time to write all this shit out. So, we have a basic curve, all right? I'm going to put it on the end over here. I'm going to put this basic curve on the end. All right? It's called a sine wave. All right? When particles go through space like photons and crap like that, they have this type of movement, but it's actually circular. So when it goes through time, it's a sine wave, right? But it's kind of circular. Okay? So maybe they're circularly polarized, whatever that is. You know, I know what it is, but anyway. So down here, this graph here, right, so it's going to be, I probably could have used whatchamacallit thing. There's a circle, and so I'm just going to put an arrow on the end of the circle, and I'm going to leave a little space there. So this is like, I may have started the circle in the wrong place. Okay, big deal. So the circle starts out, it goes around, you know, the sine wave goes around, the circle's made, and so on and so forth. But this diagram, all right, let's do a line. And so you've got this line that extends out from the origin, all right, and this line, and this line goes around like this. All right, so you've got a radius You've got a radius, it's r, which is yellow, and you've got an angle, which is theta. Okay? And you also have this one. I'm going to do a circle because it's going to be too small. All right, so that circle right there represents a point where the circumference and the radius meet. All right? That point, this is going to blow you away right here. So you have, um, um, my nose itches. We've got R. I shouldn't be doing it. I was supposed to be doing this tonight, damn it. This is going to be called, I'm just going to call it pi 1. Now, this is called, oh God, I can't even remember what it's called. It's a different type of a graph, okay? It's a radius and theta, okay? And then you have formulas that convert that information. Well, there's also what's called a real and a complex, which is a plus bj. I'm not going to go into that. That's not the purpose of this discussion. So anyway, there's that information. Now the Feigenbaum thing, okay? The bifurcation diagram that comes up. It starts somewhere, and it has this number, all right? And so the question and the problem is the origin of numbers. You've got a number. What does it come from, right? The same thing with the Feigenbaum constant. Where does it come from? So I have a theory about something, and I've been working, I want to go to the website really quick, and then, because I really got to call it quits. What I want to work on tonight is the origin of numbers, and I've got a book, actually. But there's also what's called the Pythagorean theorem, which is 3, 4, 5. It's a 3, 4, 5 triangle where the square root of 3 squared plus 4 squared equals 5 squared. It's that triangle, right? So this thing goes around, but there's also, now that I think of it, there's something else here that's missing. So what is missing? Time. Time is missing from this. And the other problem is, my theory is that the circle can never be completed. The circle can never be reached. There's an infinite number of decimal places behind this pi number, which I really hate this number. And so it just goes on and on and on and on, and it never reaches. But you can make a complete circle with the compass. So the ends eventually meet. But do they? Do they really meet? My theory is somewhere in that simple circle, there's a point of infinity. All right, and the other problem is that there's a number, there's a thing called the sine, there's a sine, a cosine, and there's a tangent. The tangent is the opposite over the adjacent. All right, you don't know about this. This is all trigonometry. So the tangent is changing, right? But there's a problem with this tangent because there's two places where the tangent equals 0 or the tangent equals infinity. Now, I'm not going to go into all that. You got to trust me. The sine and cosine represent this top curve up on the top. That's a sine wave, and the cosine is the opposite, so on and so forth. The tangent curve, so on and so forth. Now, if you take the derivative of the sine and the cosine and the tangent, you kind of get the same thing, and it's, But at the top, you've got, let me draw a line here. At the top of the curve, oh shit, I didn't do it with the straight line. You've got this, okay, and at the bottom of at the origin, that's not a straight line, but fuck it. Those lines around that curve represent derivatives, all right? You don't know about derivatives in calculus, okay, big deal. I happen to know. And so there's information around this. There's also what's called, there's stability, there's instability, where it's not stable, and there's chaos, and there's there's a bunch of stuff here about stability. So here's my problem, and here's my question. All right, I'm going to draw a blue line. All right, and we're just going to draw a line, and it's going to start somewhere. Maybe it starts at the bottom. Maybe it comes up like, who knows where the hell it comes from? But this is what it does. And we'll take a purple color because I like purple. Now, my theory is that numbers like pi, the Feigenbaum constant, transcendental numbers, have to have this picture. This is a formula. This is called a dampened wave. In a nonlinear system, there's an equation, and in that equation there's a symbol that represents the dampened wave. I may touch into that, and I may go into that tonight. If you don't know any of this stuff, you have no basis for I don't have a really good basis for my experimentation and my problem that I'm trying to solve. And I don't even know why I'm doing this. I'm just doing it because it needs to be done, right? So pi is a number that exhibits this. It has an integer. So actually, you've got the integer. Let me go to blue. You've got the integer portion. And then you've got this decimal point. And then let's do, well, it's still blue, but let's do purple. Then you've got the decimal. Then you've got the decimal portion. You can separate those. But the decimal portion goes from 0 to 9, okay? And maybe, that's the base 10 system. So it bounces. Well, I don't know if it's random. Okay, we don't know if that number is random. And so, my theory is that the origin of transcendental numbers has this information in it, all right? So let me just save this. I'm going to go ahead and drop this, and then we're going to go to Wikipedia, because I'm really going to call it quits here. And I'm not, like I said, I'm not monitoring my stream. Is it Edge Web? What is this other crap here? What the fuck is that? What the hell is on my stream? It's drawing a picture on my stream. Why do I have this extra shit on here? Oh, I see what's happening. Okay, so we'll just have to make this. I'll have to make me smaller, I guess. Put me down in the campground. This is like the origin of numbers and stuff. So you can see, like now the sine wave picture is not a circle either. It's not, you know. But here, look, they're taking a circle, and, you know, they're doing some stuff and whatever. See, that's a circle, right? But when you draw this out, it doesn't look like a circle. In fact, it can't be a circle because of the you know, whatever the hell. So it says transcendence and integers. It talks about pi, transcendental number, yeah. The decimal digits of pi appear to be evenly distributed, but no proof of this conjecture has been found. All right, so that implies a distribution. Those numbers would all, now they've calculated those numbers out to many decimal places, right? It could be a strange attractor, but it's between 0 and 1, you know. In mathematics, probes, yeah. See, it shows all the different variations of the curve and everything. I thought there was some other picture that I just saw there. Oh yeah, they're talking about squaring the circle, yada yada, all this kind of stuff. The whole problem here is pi. That's the whole freaking problem. We need to get rid of it. You know, you got things like this, you got some formulas, it goes on and on. Irrationality, nonlinearity, blah, 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 yada, yada, yada. Yada, you got an equation here, yada, yada. It comes close, you know, different ways to compute it. Yeah, okay, so, yeah, that's nice. As an irrational number, pi cannot be read as a common fraction. However, like a pi, it's an infinite series of nested fractions called the simple continued fraction, which no, it does not. These are integer numbers over integer numbers, and I don't know, they're truncating. I don't know what they're doing here, okay? It just goes on and on and on. Okay, so here's this other graph. This is the complex plane is what this is, okay? And so the point on the complex plane equals r times the cosine of theta times plus I sine theta, so on and so forth, where I is the imaginary unit satisfying I squared equals minus 1, yada, yada, yada. Then we've got e to the I over I times theta. That's like a logarithm. It's a natural logarithm, okay? It gets into logarithms. I was thinking about that because a logarithm is how you express decimal points and so on and so forth. I forget exactly how that's done, all right? So there's this aspect of logarithms, so we keep that in mind. And then you've got these approximations, so on and so forth, and, you know, so yada, yada. And then we got this thing here, and I don't have no idea what that is. The tangent number, there's all of that. There's some stuff, there's a rate of convergence. Some infinite series pi converge faster than others. There's a rate of change. Can mathematics probably choose one that converges more rapidly because faster convergence reduces the amount of computation needed to calculate. Yada, 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 yada. Yada, yada, yada. Oh, this one's interesting. This one is interesting. The Riemann zeta function. Wait. So there's all of this. There's logarithms involved, which are really not that complicated. No, someone's done this, yada, 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 yeah, summation going forever. What's that from? So on. Then we've got here 5 random walks, 200 steps. So you see what I'm getting at here. So you've got to start, and you have a formula. This is like random, but it still approaches. It's still centered around a number. So maybe we take a literal number like 3. Now it talks about the eigenvalue things, which has to do with, looks like it has to do with, you're splitting up your sine waves, okay? Look at this curve. See how this curve goes? This is a logarithmic curve right here, all right? Then inequalities and so on, yada, 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 yada. It's a long discussion. Gaussian integral, that's standard distribution. We don't know that it uses standard distribution. There's types of distributions. There's a really big-ass discussion about this stuff, all right? So now you've got Fourier. Pi, in and of itself may or may not be a problem for what I'm doing. There's the Mandelbrot set, okay? There's infinity in here, and so what we do is we investigate that infinity. But can we investigate it? And then now you've got uncertainties. This is the uncertainty principle as to a question of whether or not a part is in a particular localization or not. It represents the percentage of a part that's going to be there. So that's like saying, you've got a chance of getting some information, and then you've got the Nyquist formula, which kind of it gives you the amount of chance that you have to have a certain you got to have at least 2 times the sampling rate of the frequency you're trying to investigate in order to glean any information out of it. If it's at least 2 times, what is that? 50%, right? So we can get information right up to maybe we go to integer numbers, or who knows? But we have to talk about this. Honestly, I don't know why. Maybe it's just because I'm burned out building this project, and I need to investigate pi and find out some of the history of how it was originated, and show you why a circle is not really a circle, because when you use the sine wave, it doesn't look like a circle. If you put the circle like a sine wave, it's more like a semicircle on the top and the bottom, but that's not how a sine wave works. Why is that? Because time is involved. Time is involved. So maybe the circle itself needs to be rewritten, redrawn, with the function time added to that, so that it's not going to be a circle. It might be a circle with 2 humps in it. It's got it starts as a circle. It's got a little hump, right? It's not a perfect circle, because it's got to add, or maybe it's a dip. What is the area under a sine wave? Is the total area under the sine wave equal to the area of that circle? There's questions like that. And so that area is definitely not the same. What's the difference in that area? Can the difference in that area be explained by the fact that because you've got time involved, the circle is being stretched, it's being pulled. If there's no time, then there's a perfect circle. But there's time, and so whether it's slow or whether it's fast, it doesn't matter, I don't think. Well, I suppose it does matter. It matters in terms of frequency. So if you have 1 hertz, it's going to be slow, and the bump is still going to be there. If you have 10 kilohertz, it's still going to be there. It's just going to be there quicker, right? So we look at it at a certain frequency we can read, and so on and so forth. Yeah. Why is all of this important? It's because I need to relate infinity to some kind of mathematical construct. I also need to relate the Feigenbaum constant to this dampened wave. If we can relate an origin in the dampening equation, we can use the nonlinear, a sine wave. Is a sine wave nonlinear? Let me see here. Let me go back to Firefox. Is a sine wave non-linear? It might be linear. A sine wave is considered a linear wave because it has a constant shape and does not deviate from its sinusoidal form. Non-sinusoidal waves, in contrast, exhibit changes in shape due to factors like amplitude and interactions with other waves. Okay. Let me ask this question. Is a dampened wave nonlinear? A dampened wave can be nonlinear, especially when the wave equation includes nonlinear terms that affect the speed. Nonlinear advance from wave equation head to phenomena such as solitary waves and finite time blow up. Decrease in energy, nonlinearity. So that's the end of that discussion. I am done with the stream, and my music is all done, and I'm just going to play the music a little bit louder and end the stream on a good note. When I come back, we're going to talk about the origin of pi and find out whether or not we can find the actual origin. The actual origin. Where does pi start? Well, guess what? I got good news for you. There's another constant called phi, or phi, and it does have an origin, and its origin is 0. So pi's origin must be 0, right? How is pi created? Where does it come from? Is the Feigenbaum constant, does that start at 0? Chaos diagrams and strange attractors do not have an origin at 0. That I don't know. They have an initial starting point in this equation, and maybe that's what we need to do. We need to think of pi in terms of a strange attractor and find out if we can find an origin for it. An initial condition is what we need to do. How you like that for a stream? Yo?